Hi. I want to talk about the database as a value. So what I'm going to talk about is something that I've implemented in Datomic. And how many people have heard of Datomic? How many people have not heard of Datomic? Okay. I'm not going to describe Datomic in full. I don't have time. It's several hours worth of talks around it. In brief, it's a database. It focuses on taking the database apart and giving you those parts as independent pieces, in particular so that you can get more power in your applications by having the database as a value, which I will talk about today. It re-evaluates what should the data model be, what should an information model consist of, and decides that it must incorporate time, and I'll talk more about that. And we can do this now because we have a lot more compute power and resources, so that's why it's a good time to revisit these things. It's not new in terms of being novel necessarily, because all these ideas have existed for a very long time. So, why? Why are we doing any of this stuff? Why do we do functional programming? Right? How many people here are programming in a functional language? Or in a functional manner in a non-functional language? Okay. And what's the breakdown in the room? Clojure people, Scala people, Erlang people, other kinds, Haskell people. All right. Who did I miss? F# people we already ruled out. There was this great paper out of the tar pit. How many people have read it? All right, don't read it now, but a lot of people have not read it. Go grab it after tomorrow and read it. It's a great paper. It's really a thought piece. What they were asserting was our programs are too complex for us to get correct, and one of the reasons why is because of uncontrolled state. I don't disagree with Eric. Right, there is mutation. We need to deal with it, and dealing with it was what's important, not pretending it doesn't exist. And they proposed a suite of techniques that we could adopt in our programming that would reduce the complexity in our programs. One was functional programming. Another was more declarative programming, because even functional programming still has a lot of order in it. Right? A lot of these concatenated, functional chains, there's order inside that stuff. And that order makes it hard to rearrange things. Some sufficiently smart compiler, is supposed to do that, but we have yet to, find one. So there's interesting points about state and control, but finally, the biggest thing was the state part. And they said, we don't want to have a whole ton of mutable variables. What we'd rather have is a sound model that is an information model that we could use, and then every now and then it would change. And they chose in this paper the relational model and relational algebra. So what they imagined was a system where you would program with functional programming, declarative programming in the form of relational algebra against a data model, which was the relational model for data. But there was this missing piece, which was there was a presumption that this relational model that you were programming against somehow would become different every now and then. And it's like you've seen the comic strip, the comic, right, where there's this guy on a blackboard, he's got this giant equation, right, and at the bottom it says, and then a miracle occurs, right, and then you have a new value of the database. And this was not implemented, but it was a great piece. It came out after I had started Clojure and when I was trying to decide whether or not to stick with the functional approach, and was very inspiring for me to continue to do that. And in Datomic, what I've tried to do is tackle that last bit, which is what is the process that creates a new value of a database, and how can we actually provide that value? Oh, look, the slide comes in pieces. So how many people are in IT? Basically, yeah, all of us. What does I stand for? Information. What does information mean? This is what it means, right? You just go to the dictionary, it has the meanings of stuff. To convey knowledge via facts. Right? To give shape to the mind. And what is information? It's just the facts. Right? How many people remember the monkey before it was ripped apart? I hope everybody, or there's been a lot of drinking happening. Right? How many people could tell a story about what happened to the monkey? Good. Right? Now, you can do those two things because your brain is not pretending to be the monkey. Right? It's not the job of your brain to pretend to be the monkey. It's not the job of your program to pretend to be the monkey. It's the job of your program to maintain information about what happened to the monkey. Right? That's what it is. And in particular, we use databases to store information. Right? So we have a whole ton of complexity that comes with databases. Right? This tar pit paper says, well, the database magically changes, and then you have a value, like this big relational model that's immutable, and you can do all the algebra against it, like you can do algebra against numbers. But it has all this problem, right? It's essentially this place you go to, and you ask it for something, you get something out of it. And you go again, you get something different. There's no basis for your calculations. And again, it's the same kind of thing. If you wanted to tell a story about the monkey, and the part of your brain that remembered the monkey was just like being trashed by thoughts of, I don't know what, some computer game. You couldn't do that. You couldn't reason about the monkey, right? You couldn't do your talk about the monkey if you couldn't go back to some basis that was shared. Remember the monkey that was all intact? Okay, well then this happened to it. What if I had done something different to that, right? If we don't share some foundation, we can't carry out a logical argument. And this isn't about logic or something fancy, right? If you have a business, you can't make decisions if you don't know what happened before yesterday. You can't. But we have this problem. We can't go back. We can't get any basis. We actually can't. We're not correctly implementing memory. That's our problem, right? And we're not going to get there by pretending to be the monkey, right? That's not memory. Other problems with the database is it's remote. So we have this communications problem. That leads to a bunch of issues. And the notion of what is an update is poorly defined. So what do I mean when I say basis? Well, I sort of talked about this, right? It's how we do calculations, right? You can say there's no such things as values, and anything could change at any time, but you really could not define any mathematical algorithm or anything else or any decision-making process if in the middle of that process the things you said were the foundations of a prior decision have changed in the middle. If 42 could change into 57 in the middle of calculation, if registers in the computer just had quantum effects randomly changing them, you really couldn't get any work done. So we need this basis. And in particular, we're going to have multi-step operations, and we may want to revisit the basis more than one time and have that revisiting mean the same thing. Anytime we have the notion of simultaneous change, this doesn't work. It's not to say that there isn't change in the universe, right? But when we're trying to think, we actually need something stable. When we're trying to make a decision, we need something stable to use. And that I'm going to call the basis. Right? And we have this problem also with databases. Update, what does it mean? What does it mean? Right? Does an entire row replace another row? Is it a column thing? Does the whole document replace a whole document? Can you replace one part of a document? If more than one person is doing this at the same time, what's happening? Right? What are the semantics of update? It's very tricky. Right? Now, traditional databases have gone to great lengths to try to define as-if sequential operations and things like that. So you can start to reason about it. We're starting to discard all that as we adopt NoSQL. We say, oh, well, whatever. More than one thing is going to happen, and it's eventual consistency. Like, just by saying that, we're good. It's going to be fine. Eventually, it's all going to be good. Right? That's just a lie, right? It's a lie. And then what can we see while this is happening? I'll use the word perception a lot. What can we observe? Because if we couldn't actually see light rays, right, bounce off the monkey, if as they traveled back to us, they got all scrambled, right, if we couldn't observe a consistent view of light coming off the monkey, we couldn't even have experienced his whole little presentation, right? What do we see when we see things? One, we see the past. Right? We don't have a live connection to the monkey. Our eyeballs are not on the monkey. Right? We see the past. What else is characteristic of our neural systems? Are they continuous? No. Right? They save up stuff. These light waves are like, woo! Maybe they're quantum, right? We don't know. But something wave-like is happening. Right? It's hitting our eyes. The retina's going, wow, and the nerves are doing what? Are they going like this? Woo! No. They're going, doom, 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 doom. They're taking pictures, right? Big simultaneous snapshots, right? And that's what we're storing in our memory. We need that. That's how we work. We're trying to build systems. If you want to emulate anything, don't emulate monkeys getting torn apart. Emulate brains, because brains are more powerful than stuffed monkeys. So what happens? We get wrong programs. We have problems trying to scale things. We're afraid of all the round trips to the database. Ooh, I better go once and make sure I do everything I might need to do. We're afraid of overlaying the server, right? Because we co-locate all this stuff, right? We have this big database server brain that does all this. But it really leads to programs that are poorly modularized, right? Right? You're going to have one part of your program that decides, we should talk about this person, you know? Another part of the program that decides, well, it's going to go on a screen, and the screen should show the, you know, the email and the whatever. Who writes those two parts of the program? Different people, I hope, maybe, if you have a big enough company. Right? Who writes the query that gets this data? Different people? No. Right? You're trying to shovel this one query through these two conversations through one query because you're afraid if you issue two queries, what are you going to get? Things that don't match up because you have no basis. So we have poor modularity. So we need to pull this apart. We need to answer the coordination question. Obviously, some coordination is going to be required if we don't want eventual consistency magic. You know, we need to eventually decide to coordinate. That's what needs to be eventual. We just need to decide where that happens. Processes require it, but perception does not. Perception should not require coordination. And almost all the time it does, and that's wrong, because that's not how it works. Right? That's not how perception works. That's not how we saw the monkey. Anybody ask the monkey, send me your image, get your view of the orange. Anybody do that? Were you all like sending messages to the monkey? Yeah, please give me whatever. Did anyone register for updates from the monkey? No. That is not how it works. It's not how it works. Right? Light bounces off the monkey has no say about it. It comes towards you. You can open your eyes or not, but that's all just going to happen. Right? How do we model that? Right? And then we get back to the value problem. Right? If you can at some point get out of the state and say, I can get something that's immutable that I can think about, you can't really have a conversation beyond that. It's just like, well, everything is fuzzy and changing, and there's no way we can ever make a sound decision. There's no way one person could convince somebody else of something else. There's no way we could add up our books or calculate what our interest rate should be or anything else. We'll just stop. So we got to reach immutability at some point. All right, so I'm going to talk about value. When I say value, this is what I mean, something that's immutable. The definition in the dictionary starts with small things where we all know this. 42 is a value. Right? We've already scaled that up, right? In languages people are using, and how many of your languages is a string of value now? Most, right? How many people are using languages with mutable strings? Right, sorry. Most of you are not. And then you can get bigger, right? Dates. Eventually Java will learn that dates are immutable. But GOTO time has learned this, right? And it can get bigger still, right? Collections can be immutable. Entire collections, right? How big can we dream here? Could we make an entire database immutable, or effectively immutable, or appear immutable, so that we could, for instance, see it? So that we could, for instance, remember it? Let's try it. When I say identity, I'm talking about some blank thing. Oh, that. I'm talking about some logical notion, and it's not necessarily the name, some logical notion that we apply to a sequence of values over time. Right? It's not to say that this entity that we're thinking about doesn't change, right? But there definitely was a time when the monkey was all together, and now the monkey is different. And we can remember those different times, and we can process them. And we want to make programs that can do the same kind of thing. So we're going to say the state is a value of an identity at a point in time. And a lot of what Eric was talking about, you could say we're like identities, right? If you can go to that lazy and ask for the thing out of it, right? The lazy might be the identity, and the thing is the value you get out. Or if you can ask for enumerable for the next value, and you talk about those kind of values, then that enumerable thing is acting more like an identity. And time is just this relative thing that we don't know a lot about. So we have this model we could use. We could say an identity is just a succession of states. Each state is a value. Right? The real world case of, does the monkey stay around there? No, but our memories of the monkey can stay around there, right? That's what we're talking about here. We need to make programs that can remember things, and we need to make programs that can see things. So we're going to use functions to go from one state to another. We'll associate identity with that whole thing, and we're able to perceive. The important thing is the perception is uncoordinated. You can just see it's like light. You don't need to say, stop, wait, Eric, don't do anything so I can look at the monkey. Now, okay. So we know how to implement values in programs. We use persistent data structures. I don't have a lot of time to talk about it, but basically they're trees, they're structural sharing. We're not talking about persistence on disk. We're talking about immutability and efficient change, right? And so the technique that's used is you represent your data structures as trees. When you want a new version, you don't copy the entire thing, right? You copy as little as possible, and you share structure with the old version. And that allows this one to be immutable and the next one to be efficiently created. This is how we do it in memory. One of the things that this talk will be about is what do we do on disk? What do we do when we want to make this storable? So I think we can go back. And that original slide was from a talk where I was talking about something else. Objects. It's amazing what happens to slides when you give them to somebody else and they put them together in a thing. This mutability stuff is awesome. I drew that original diagram in a talk about objects, right? But it ends up that the database is this big, nasty object. It's this big object we all have to contend with in our system. It's this place we go to, right? We say, please, please change somehow. And like something happens inside. And we go up to it and we say, oh, please, please tell me the answer to this question. And it's like this oracle says, there's the answer. It's like that. It's a big object. And what's critical here is, what can we remember? Nothing. If we applied our function to something, what do we apply it to? Who knows? Consistent read, eventual reads, serializable. Who knows all those things really well? Yeah. Great. Not working. So what's missing from this diagram from what we had before? That stuff. Wow, this is great. Oh, 2 talks in one. Because that was an image. I couldn't erase the image, so I was the programmers do not know how to use Keynote very well. So we can say the same. We can say the same thing about the database, right? Except what is the identity? The database connection. Before, in a traditional database, right? That database connection, it is all we have. It's the thing. It's the totality of what we know. It's like an object, right? It only has methods, query, answer, change, or something. That's it. This connection is the only thing we can manipulate. We can only write functions of the connection. Functions of the connection. That's how we do change. Functions of the connection. That's how we do queries. We don't want to do that. We want to do this, right? The database connection, it's still there. It's the identity, right? Yeah, tomorrow if you go ask your database for its value, it's going to be different if your company is still in operation, right? And you had power overnight. You should expect a different answer. That's okay, right? Stuff does happen in the world. Process happens. The world does move forward, right? But do we really want to be writing functions of connections and queries against connections? No. We want this good stuff inside database values. Because if you use this as the identity this way, right, what is your function a function of? Whatever serializability mode you're in. Right? What is a query a function of? Whatever the state the database is in, right? So it's a function of string to what? Result set, or something like it. What can you do with the result set? Not a lot, right? You can walk through it and print it. Right? It's not a really rich thing. If you could get the value of the database out, what could you do with it? You can query it all friggin' day long. What else could you do with it? What else can you do with values? What can you do with 42? Apply functions to it. What else? Not have an ORM. What can you do? How about communication? What can you do with it? Can you email it to your friend? When he gets it, is it going to be 57? No!
If he's little at the end.
Maybe, right? So it would be nice. Also, it would be a lot easier to reason about applying functions to the value of a database than the value of a database connection, right? We'd like to make transformation functions against that. So how can we start talking about the database as a value? Right? The first thing we have to contend with is this notion of state, right? Because everyone knows databases change, right? Change. So they do. And so the question is, do they change in place, or do they change by growing? For most traditional databases, what do? They change in place. They pretend to be a monkey. That's awesome, right? They forget everything they ever knew every time you tell them something new. It's great. They're great decision-making tools. How many people keep your source code in a directory, and every time you change a file, you just overwrite the one in the directory? Yeah, we're doing that, right? No, we're programmers, and we know what we need. What do we need? Every friggin' version we ever made, right? And what's on every version? When? It grows. Anybody care that their Git repository keeps growing? Everyone's like, no, we'll start overwriting that. My disk is filling up, dude. No. Why did we ever do that? It's really not an information system. A database that updates in place is not an information system. I'm sorry. A real information system should accrete facts, right? It should accumulate, because that's what happens in the world. Yes, stuff happens, but an information system needs to keep gathering the stuff that happens, not, pretending to be the world. It's supposed to record information about what happened in the world. Right? The past does not change. If you're an information system, you have to record what happened in the past. You don't go back and fix it. You don't change who the president was by typing in Obama over Bush. Right? That's not what happens. That's not what happens in the real world. That's not what should happen here. So if you have process, right, change, and you're trying to build an information system, you should acquire new space to record new information and move away from using places. So how are we going to do this? And this talk is just like about a slice of Datomic, and it's about the idea of making an accumulating database, but also a little bit about how. That model I showed before that we use in memory, right, with a new root every time there was a change, right? When we do persistent data structures in memory, every time we change, right, we end up with a new root. And usually we forget about the old root, because often there's a single thread of control that cares about the transformed values, and the old values, get garbage collected. But sometimes we could remember them. But the only way we could remember them is by having been there, right? In other words, if you're using persistent data structures in memory and you never saw this value and now you're looking at the later value, this old one is unrecoverable, right? You can't do it. But if you're making an information system, the past should be recoverable. So we don't want to store a root per query, both because it doesn't let us find that. We'd have to have a way to find the roots, which means another meta mapping to roots. And the other thing, it's way too expensive to do. Right? So instead, what we're going to do is we're going to have this value that just gets bigger, like the rings of a tree. Is that still a value? It's a little bit tricky, right? Because now it's a bigger tree. But one of the things about a value is, if I saw X and I go back looking at X, is it any different? If you could say of the inner rings of a tree, I've made a decision based around the inner rings of a tree. This is what's happening to the weather. And then you send a view of the inner rings of a tree to your fellow tree scientists. And they want to look at the same thing. As long as the inner rings of the tree have not changed, like maybe 5 years have passed. Right? As long as the photo you took is still good, like people weren't erasing it and drawing a bigger tree over it, right? Then they could make an independent decision later. So I'm going to contend that an ever-accumulating value is still a value by the definition I gave before. So Let's talk about facts. Again, it's this word stuff. These words, words. The dictionary has an entry for fact. It says this: an event or thing known to have happened or existed. Right? And it's actually from a past participle that's Latin. That back when, they knew what they were doing. And it means something done. It is a fact that says it's about the past. That's what fact means. It's something that happened. It's about the past. And it has to include time. Right? Sally likes pizza. It's an insufficient fact. Right? She used to be lactose intolerant. Right? Then she got cured, and now she likes pizza. Right? It's not an eternal thing that Sally liked pizza. There wasn't always a Sally. She might stop liking pizza. We're not going to pretend to be the monkey here, right? We're not going to go to the Sally place and change this, right? At some point, Sally started liking pizza. At some point later, Sally might stop liking pizza. These are facts. We can record all these things, and we can make decisions about what happened in the universe. So we want to record facts. So what's our structure? What's a fact? Is a document a fact? A whole document. Is that a fact? Is it something that happened? What happens when you want to change it? Did you change the whole document? No. Right? It's too big. How about a record in a database? Is that a fact? When did the record happen? And if you update one of the fields of the record, when did that happen? What's the time of the record later? How many people ever tried to build a system that kept a last edited date on records? Everybody does, right? How many people thought that was a good time? Yeah. No. So if we want to make a system that records facts, we need to boil down what a fact is. And in Datomic, the name comes from the word we use for this, which is a datum. It's not a new idea, right? Entity, attribute, value. Right? Sally likes pizza. And then what? When? When did Sally like pizza? Right? And we use the transaction to encode that as opposed to the time of day. And there's a bunch of other reasons, because transactions are first class, and we can have facts about transactions, like who said that Sally likes pizza? Or where did I find that data? The other thing we need to do, if we want to make a system that can manage information about the world, is we need a way to represent process, right? The fact that the monkey had its head and arms torn apart, right? What is the representation of that fact happening, right? We can say, the monkey had its head on, before the talk, and then, then what? There'll be a new fact, which is at a certain point in time, the monkey did not have his head on, right? But our information system is going to need to have that information sent in, right? So what's the representation of process, of that change? How do we form that? And we're going to say that a primitive representation is just the assertion and retraction of facts. Monkey has a head. Monkey's arm was torn off. Monkey's leg was torn off. We're just going to assert these things. If Sally likes pizza and then becomes lactose intolerant, we may have to retract that. That's okay. And this is minimal, but it's insufficient. Right? Because we know there are transformations that happen in the world, or transformations we'd like to represent in our business, that we can't express by just saying, your bank account balance is now 1,010. We really want to say is your bank account balance is a function of what it was plus 10. Right? But we can apply those transformations and then turn them into these. And this is what we end up with at the bottom. I'll show you how that works in a second. So fundamentally, what we want to do is take the database apart. Right? Try to get the value part out. There's other aspects of the system I'm not going to talk about much tonight. But if you look at a traditional database, it's doing a bunch of things, right? It's doing transaction management. It's doing I/O. It's usually in charge of local storage, right? It does indexing, and it has the query support. This is what we call the traditional monolithic database. And there's a way to split this apart, right? Because I think this split is really important. There's a process side to a database, which is recording those transactions, accepting and recording those transactions, right? And possibly organizing that information for other people. And that's, the output side. The database is going to spit this stuff onto storage. And then there's a perception or reaction side, Right? And it's not that the reactive stuff is bad. In fact, Datomic has a push-based plug-in, call me when new stuff happens. But there also should be just straight perception. I just want to look at the database. I want to ask anybody's permission. I want to coordinate with anybody. I just want to look. It should be like light. I should just be able to open my eyes and see stuff. And that part incorporates both query and, by implication, the consumption of indexes. So we like to take this stuff apart. And there's a bunch of reasons to do that. One is scalability. The other is to address a bunch of the complexity things before. And the point of this talk is to give that value of a database to a program. So I'm going to contend that if what you're using to store data, another completely empty word that we use, doesn't organize it, it's not really a database. Right? It's like a bag. Right? You put stuff in a bag, like you can't query the bag. You just have to fish through it. Right? That's not a database. Right? Key value store, it's a bag. It's not really a database. There's no leverage there. Indexing is what gives you leverage. Organization gives you leverage. So what we're going to say is that a way to organize these facts is just to sort them. And simple sorting, it's a powerful tool that we use. That's why we have computer science, right? They invented sorting. But it ends up that this is a hard thing to do, right? In particular, if you want to have an immutable set of values for your database, right? You cannot afford to sort live. And in fact, a lot of databases can't afford to sort live, even when they're update in place. Right? Live sorting, live indexing is a huge source of overhead for databases. And there's great research from Yale and other places showing we're wasting a lot of time around that stuff. But we have good examples, one of which is Bigtable, of how to do this better. And the way to do it better is to do it in batches. Right? You accumulate change in one accessible area, and periodically you put that stuff into another area. And anybody who wants to see everything merges these two things. In the case of Bigtable, they do take an immutable approach to storage, which means they'll accumulate stuff in memory. Now, they're also logging it. So this isn't about durability. Just because they accumulate in memory doesn't mean if you pull the plug, they forget everything. They're logging. But the information model is a combination of what they've accumulated in memory and what they've put on disk. And so what they do is they build up a block in memory, they sort it, and then every now and then they take that block and they just spit it out on disk. And after they've done that, they never change it. And then they'll get another one. They put another one on disk. Now, at the point they've put the second one on disk, if you want to see everything, what do you need to merge? 2 files on disk and whatever's in memory. Every now and then they get enough things on disk, and they say, let's merge all those into a bigger file. Once they've done that, if you want to see everything, what do you need to merge? That bigger file and what's in memory. And that's it. So this principle is a sound one, and it's very efficient. Right? The only thing that Datomic does differently is because we're trying to give all of history and do that efficiently, and there's a bunch of other storage-related things, we're going to use persistent trees on disk instead of ever bigger flat files. So this looks like this. There's some process in charge of transactions. In the case of Datomic, because we split everything apart, we can make independent decisions about the scalability, consistency, and availability of reads and writes. And we actually make traditional decisions about writes. Right? Single server. It only accepts transactions. That's all it does. And it keeps a live index, which is the novelty. It logs to storage as it goes, just for durability purposes. But every now and then, in the background, a process called index merging will take the stuff from the live index and merge it into a persistent tree on storage. And then you can forget the live index and start replenishing it. So you just have a small window that you accumulate. Just like the Bigtable model, but with the trees that you saw before, except instead of having new roots, we're going to have one big root every time we do an indexing job as opposed to every transaction. And the tree will have everything that ever happened, not just the latest. And then what is perception like? Well, perception is just this merging job, right? If you have access to this live index and access to storage, you can see everything. Any coordinator in here? Transactor's not here. Is there a server? No. Just like there wasn't one governing our looking at the monkey. Nobody's in charge of that. We can all do it. If we have the rights to storage, we can all do it. So this is the high-level view of the architecture of Datomic. We've taken all those bubbles from the monolithic server and we've spread them around. In particular, we've moved storage out. We said that is just commodity, key value store, old-style database. I don't care what you want to use. Anything that can let me put a blob in with a name and get it back. It's not a database. It's just storage. Right? It's like, squirrels hiding acorns. If I can find my acorn, I'm good. That kind of a database. There's a transactor that just does transaction processing. If you want to keep it highly available, you do what you used to do for databases. Just run a second one warm, right? But this is the key thing. The application process has got query in it. Right? App servers have query in them. They have the query engine in them because they can access storage themselves. The other thing the transactor will do is reflect change so that everybody who wants to play, we call them peers, has their own view of the live index. And they all do the same thing, right? Once the new index has been merged, they're told, and they say, OK, do over, start over, just drop that. And they're always merging these two things. But now we have potentially horizontally scalable storage, right? This could be DynamoDB, right? Any of those big, massively redundant, highly available things. And query is now horizontally scalable because we can just add more app servers and get more query capability. And what query is being presented with is not objects. Now, so what's the difference? In that old database, when I talked to the Oracle, right, what could I get at best? An answer to one question. What do I get here? The source of all answers to all questions. I get the power. That's what I want. So the memory index is pretty straightforward. It's a persistent sorted set. It's like a persistent B tree. And you have pluggable comparators, and we always maintain a couple of sorts. Entity-oriented, which allows you to treat the database like it was objects, except they do have history and everything else. They're not just, pretend to be the monkey things. And you have attribute-oriented indexes, which allow you to treat the database like a column store. It's very important that you can slice the thing two ways. If you only have objects, you're just crappy at queries. You can't answer basic questions because it's like a million objects, dude. I can't ask a million objects for their name. I don't have time. I want something that has all the names. And that's what the other index does. And there's also kinds of other indexes you can ask for. On the storage side, there's a log, and again, that's just so that you get durability as you go. But the fundamental thing is that there's going to be these covering indexes, and they're represented on disk or in storage as trees. So what the storage engine will do, what the database will do is treat the storage engine like a key value store, just like a traditional database treats the file system. Right? A traditional database stores what in the file system? Does a little file with like your name in it? No. Right? What does it have? Blocks of its indexes, index segments and nodes. That's how it uses the file system, right? And that's the way Datomic uses storage. It doesn't matter if you're using a SQL database. We don't store Sally Likes Pizza in a row in a SQL database, right? We take a big chunk of our index and store it in the database under a key. That's why we can use key value stores or SQL databases. So the requirements of the storage system are very minimal. You must have key value access. Occasionally, we need consistent read. And very occasionally, we need conditional put. DynamoDB satisfies this, and SQL databases satisfy it. And hopefully, we can get things like React to satisfy it as well. In memory, the database value looks like this merge, right? There's this live memory index I said is a persistent tree. Then there's the one that's backed on disk. What's really cool about this is that lazy value thing, right? Is the entire database on your machine? No, this is not full replication. Every peer doesn't have every database. Every peer has access to storage, right? And if and only if you go and ask about some particular thing and you don't yet have it, and it's not in your cache, and it's not in memcache, then you go to storage. Now, how can we do all this caching? Aren't we afraid of monkeys exploding in place? No. Why not? It's all immutable. It's the facts. You can't change the past. It's all the past. So we can remember it on disk. We can stick memcache in between there. You can have a local cache in between here. And then it ends up that stuff is zipped, and it's zipped here, and you can remember it unzipped. I don't really care. You can remember it all you want. You can stick proxies in between. You can put your database behind a CDN. Why can't you put your database behind a CDN? You should be able to. OK. And then there we have this thing. Look, those things from before. The identity. There's this one little CAS thing. One CAS. That's as much mutability as you need to implement a database. One CAS cell. One. And it's got a pointer to an immutable thing and a pointer to another immutable thing. Right? And yeah, when this new process, this has grown, and this CAS gets a new one of these. But if you were thinking about the old one, it did not have its head ripped off while you're in the middle of calculating. Did not. Will not happen to you. And if you told your friend, the scientist, could you please look at this weather data? How many people have ever had a system that exhibited a bug, and after you added more data to the database, it went away? Yeah. Happened more than once for me. How many people would like to have gone and said, what was happening at 2 o'clock to your database? And ask the same question again. And then be like, wow, yeah, that is the wrong answer. And then fix your code and run it again against the same version of the database and say, fixed. Woohoo! As opposed to doing what? Trawling through logs and hoping there's some evidence of what might have happened. Right? We don't want to do that anymore. We really do want this. The index storage is not terribly interesting, but it's a tree on disk. Right? There's 3 levels. There's a root, which points to directories of segments. And the final segments are just sorted datums. They're blobs. You can think of it like B-tree nodes, except B-tree nodes save space so you can mutate them in place. But that means you can't cache them. Right? There's trade-offs, right? It's not like all cool. There's trade-offs, real ones. All right? So I said before, you can't express transformation, so we support something else, which is a transaction function. It's a cool function. Look at that argument. That's not the connection to the database. That's the database value. Right? You get past the database value and any arguments, and you return new facts or new database functions. And the transformation happens iteratively until everything's been replaced. And so eventually the process bottoms out into a bunch of assertions and retractions. That looks like this. So you have assertions and retractions and maybe a database function, and that will be applied. That yields 2 more database functions, and eventually it all turns into assertions and retractions. There's no more functional transformations. But each time they get past the database. And you can do whatever you want. You can issue queries. Right? How many people wish SQL databases were more functional and composable, and you could really write functions that return result sets that you could pour into other queries? Yeah. That's what it should be. You're not wrong. You're right for wanting to have that. The transactor accepts transactions, right? It expands it just the way I said, right? It actually applies it to the old value of the database and gets a new value of the database. It tells people who cared, this was the new process. It does not send the whole database to everybody. It sends just the change. Monkey had head ripped off. 640. That's it. Not a new monkey document. Right? The fact. Right? Every now and then, so it broadcasts that back to peers, and there's indexing in the background. Unsurprisingly, indexing creates garbage. It's just like what happens in memory. Right? How many people work in a garbage collected language? How many people want to go back? Yeah. Right. Okay. All right. Then we have the peers. Right? The peer, it's a great word. It means I trust you as much as I trust anybody else. We're like equals in this. Right? That's how it should be. It's not like, oh, please, database, give me the right answer. Right? It shouldn't be like that. We should all have equal power. So you do. Any peer has access to the storage service. Peers have their own built-in query engine. Right? And the query engine is really kind of an orthogonal thing. I mean, it happens to be the case that Datomic ships with a data log engine, but you could have any number of query engines. It's orthogonal. Right? They have the access to the live index, and they know how to merge. Caching out the wazoo, right? Local caching, caching in a local memcache, then a shared memcache cluster behind everybody else. And then finally, whatever Dynamo does or whatever a SQL Server does. Or you could cluster Postgres. I don't really care. Do as much as you want. It's very straightforward. Right? So what happens after we do this? I mean, why do this? It sounds cool, though, right? Because it's simpler. Because programming against connections sucks. It just sucks. It's not great. It sucks. It really does suck. Right? So we want this epical state model I showed you before. We want to limit the amount of coordination we have to transaction processing. We want direct perception. Right? We want to be able to reissue the same query. We want to be able to say, I found the guy we should be reporting on. It's Fred. And then somebody else say, I need to show Fred on the web page. Give me his email address and whatever. And not be like, oh, I don't know what Fred is anymore. Fred quit. You know? Or, you know, I can't make a total of all the sales for the month because I can't issue more than one query to do that per department and get a total that adds up. How many people want to work with an accountant that uses a ledger where he erases stuff and writes new stuff in? Yeah. So we have the stable basis. You can communicate a point in time of the database with a long, with a transaction ID. You can say, I think I found something weird in the weather data at this point. And you can send it to somebody else. They could look at it 3 months later and see what you saw. Just like you took a picture. Just like you remembered the monkey before it had its head ripped off. Same thing. So you have this basis. And a transaction is well defined. It's a function of a database. Right? What else happens? We have I said this already. You have the communicable basis. Right? We can move anything around that we want. Right? We now have this ability to disentangle where things are located. You can start in memory. You can use a local disk. You can put it in SQL Server. You can put the same thing in DynamoDB. Don't care. Right? You run your peers wherever you want. Run half the app in the cloud and half the app locally. Does not matter. Then the big payoffs, right? The big time payoffs. The database as a value not only means that you can issue queries yourself, but it means that you can talk about those inner rings. You can talk about the past. Right? Just like we can talk about the monkey before it was ripped off, and you can tell the story of it, because you can go back. That's what memory is. That's what you want your programs to have, memory. Right? You don't want them to be simulations of everything. There's places for simulations, and there's parts of your programs that will behave like machines. And mutability is great for that. Right? But for information processing, we really would like memory. Right? Which means that we can go and say, I mean, this is a function of a database that yields a database. Value. Right? Yes, you will talk to the connection. You'll say, give me the database. Then you can say to that database value, show me what you looked like 2 months ago, or at 2 o'clock when we were having that problem. Give me the database as of 2 o'clock. Give me the database since this point in time. Give me the database as if I made this change. Anybody ever want to see what a speculative change did and tried to do it with rollbacks and stuff like that? Anybody piss off your sysadmin when you were doing that? Yeah. That sucks. That's not right, right? So now you have database value in hand. If you want to see it as if you did something else, what do? You just do it. It's a value. It's all you. You don't need to talk to the transactor. You're not actually saying, I'm doing this. You're saying, what if I ripped the head off the monkey? Would it weigh less? Yeah, look at that. A monkey without a head, I add up the components, and it weighs less. That's so cool because I can fit more headless monkeys in a truck. Let me go do that. And then then really do it for real. So you can do as-if things. The other thing is you can do queries that compare times and cross time. Right? This is what businesses need. How many people are doing big data on logs? Yeah, or think they might need to and soon. Yeah. Why? Because your business is telling you, that database you gave me, it sucks. It forgets everything after I tell it anything new. We need to go look in the logs, because the logs have everything that ever happened, and it doesn't forget anything. Let's start writing big data apps. Big data. Let's go do it. So you can write a query that crosses time. How often has this supplier changed their prices? If I only knew their latest price, I could not answer that question. Right? How many people would like to think, how good would your decision-making process be if you forgot every past value that you ever knew? It would be terrible, right? Most business decisions actually involve the past, right? Involve deltas between things or rates of change. So you need to be able to query across time. as of different points in time and across time. So you can do all this stuff. Right? You can issue a query that takes forever. Anybody issue a long query? Took a long time? Again, was the sysadmin happy with you? No. If you're doing this and you issue a long query, who does it impact? You. That's beautiful. Want to run long-running analytics? That's fine. Right? Want to figure out if a query is really expensive? Go have at it. Run it on a spare box. Right? So the net impact here is this is just completely different. It's super, super simple, and it really reduces the complexity in your applications. It gives you a lot more power, right? You're not handed, the function of a database isn't a result set. It's a real database. You can query yourself. You can scale things better. We saw scalable reads and scalable queries, and it's a real information model. That's it.
Now you got a question?
Yes.
I like the way you seem to talk a few times, Rich. I like the way you boiled things down to English definitions that are clear and concise. I got confused on one of them, though, which was you were talking about a value as being the accretion of all the values that happened in the past, and we can still call that a value. And in the beginning, you talked about an identity, which were things that were this sort of pseudo thing that was this linking together of causally related.
I will repeat the question.
So I got confused as to what the difference between those two.
Okay, so the question is, I talked about a value as an accretion, right? And I talked about identity as sort of this putative entity, right? So the identity is the database connection, right? I want to go talk to our company accounting system about our balances. So the company accounting system is going to be some system, and it ends up that a system in Datomic is not like one server, but it's the combination of the transactor and whatever the storage is, plus the name of the database. That whole thing is the identity. Given that identity, you can go and ask for the value of the database. As soon as you've done that, anything that happens out there, it doesn't impact you. It can't impact you. So now the question is, what does it mean to have an accreting value, right? So the first thing is, once I have this value in hand, it's not going to accrete. Right? The thing inside the connection is accumulating new information, but this is not growing. The other thing is, if I communicated this to somebody, if I said, check out the answer to this query against database, I would be communicating to them two things when I communicate a value. One is where to come from, but the other is that T. It's being able to talk about that T that allows you to recover later. So I say, 2 o'clock we had this problem. When I communicate that database to you, I'm going to say the identity of the database and just a T. With those two things, you can recover a value that's the same value that I had. In spite of the fact that the thing inside that identity is now bigger, if we look at the inner rings of the tree, they're the same.
Brisbane asks, can you handle schema changes?
There's hardly any schema to change, right? So can we handle schema changes? What schema? Where's the record definition here? Document definition. Nothing. It's atomic. There's almost nothing to change. Yes, you can rename attributes. Because the only schema definition there is attributes. Of course, there's always an implicit schema, right? But what matters is, have you married an explicit schema, right? Relational databases definitely have a problem. You need to know this is kept in that table and that's kept in that table. And if you ever need to connect those two things, you better know the name of that other table, right? Furthermore, table names are not first class. They can't be components of queries or anything else. So, yeah.
Other questions about active?
Yeah.
How do you deal with coordinating updates? So if you've got two things that want to update an identity, how do you deal with that?
So there's a transactor which coordinates everything. It's strictly serialized. You can imagine it as a single observer of the universe. And if you're talking about coordinating, for instance, if we both want to increment somebody's balance, you would use those transaction functions for that, right? Rather than each of you asserting, the new balance is 107, you would say, I think the new balance should be 10 higher than what it was, and I think it should be 5 lower. Those two things commute, right? And therefore, it's fine. So you use database functions that are commutative, and you can have things that merge transparently without any eventual consistency. But of course, there's a definite trade-off. I'm not saying there aren't times, there are times when you have to choose eventual consistency because of your availability or right scalability requirements. So this database is definitely sitting at a point in the space, which is a big space, that says you are not going to exceed its write capacity and you value the transactionality, but you want the read scalability, which I think is a different place from a monolithic database and the free-for-all that is key value stores.
Last question over here.
Yeah.
From the developer perspective, what implications are there for querying the data, for issuing a query?
Implications for issuing a query.
Yeah, from the developer perspective, as opposed to a SQL or NoSQL database.
So again, I said the query language is sort of orthogonal. I'm not talking about it here, but the query language we include is called Datalog. And it's really easy to use. It looks like pattern matching, if you've ever seen pattern matching in any language. And the joins are implicit. And we also offer you more control over what happens. I'm not a big believer in sort of the magic box. Query planner will solve every problem because it's too hard. So you do have more ability to drive it. But you also can get direct access to the indexes and build your own query engine. I'm happy to see it. And for instance, CoreLogic from Clojure can use this as a backend.
Great. Both Eric and Rich are going to be around for a little bit before we drag them off and put some food in. Perhaps we could show them both our thanks for making the trip and giving these great talks tonight.